I think you all know Mr. Lee Garlock. He's been in the club for quite some time, and he does some interesting presentations on antennas, and has quite the resume behind him. So he's going to be talking tonight about antenna modeling. So I'd like to turn it over to Lee and get him started.
Okay, so let's see here. Hopefully my share screen will work. And let me go to, yeah, the slide, slideshow. And, okay, everybody got that? We okay there, Andrew?
You look good to me.
Yeah,
okay.
Looks really good, Lee.
Okay.
Yeah.
So let's talk about, well, let me talk first, just an intro real quick. You know, we had a little discussion about antennas with the previous meeting, and about how to model, and Mike showed a little bit about his modeling, and this is a modified version of a presentation I gave back in February to the Quarter Century Wireless. And we had done something years ago to Vienna Wireless as well. So let's start with our basics. There are lots of different ways you can model antennas, depending what kind of antenna it is. If you want to do a model for a large dish antenna for EME or something, you're not going to use the techniques probably we're going to talk about here. You can, but the number of segments for a very large antenna get to be very large. And so it all has to do with the size relative to wavelengths. So if you have huge antenna compared to a wavelength in dimension, then you probably want to use a quasi-optical technique. And there was, and I'm not sure if you still get it or not, but there was something called GRAPS that had a student version from a company in Denmark, was a pretty good one. And there's a lot of other techniques, physical optics, uniform theory diffraction, NEC BEC from Ohio State, lots of stuff out there. But if your antenna is not relatively large to a wavelength, which is true of most of our VHF, UHF antennas, then we use a technique that actually involves solving Maxwell's equations, which are generally called electromagnetic computational code. And there are a couple of different techniques. The best known one is something using a technique called method of moments. And it's linear algebra based, which is kind of weird. It's like, you know, the variable is part of your equation. And anyway, and that is generally referred to as NEC. There's NEC 2, NEC, which was the original, one of the original versions that's in the public domain. NEC 3, NEC 4, which is not in the public domain. It belongs to Lawrence Livermore Labs. You have to have a license to use it. LNEC, there's Super NEC by a company in South Africa. Mini NEC was made by two scientists at the Navy in San Diego, Jim Logan and Jay Rockway. And then Magna Gao is very popular in Europe and is actually a rewritten version of Mini NEC. And there's also ez-nec, which showed up in, you may have a copy of that if you have an ARRL antenna book, because they included it on the CD. There's other techniques, transmission line methods, finite element, finite time, difference time domains, but we're not going to go there. So where do we get this software? You get this wonderful free software at the address link here, www.qslnet.net/4nec2. There's a lot of tutorials out there on the internet for you. I've listed 3 of them here that are guides for using 4nec2. 4nec2 has some interesting programming things. Were included in the code by the developer over in the Netherlands. It includes the ability to use a variable rather than a fixed value, which lets you make readily quick changes in dimensions and things. Instead of having to rewrite all the numbers in the columns in the input file, you can just use the variable and change it once. There's also some facilities in there for optimizing your antenna. And when you download this program, you will get hundreds of antenna design files already with it that you can modify, look at and give you a good idea how to use it. And so the other versions of NEC I listed here, the MMANA-AL, there's a freebie version of that that's widely used by Europeans. It's basically in Germany. So that's where you can get it. And again, for what we're talking about, the program, this is the top one up here is where to go to get it. So it uses it actually solves Maxwell's equations, which are listed here, but you really don't have to know anything about any of this. But that's the underlying behind it. So what you should know is the way it works is it takes the geometry you put in there as a description of basically conductors, wires, broken into little segments. You tell it where your excitation point is, which normally for most of the stuff we're doing is 1 volt at the feed point, although it can do actual receive incoming waves and other things. And what it does is it sets up and solves for the current on each little segment of a wire. And it does a discretion here because the current on each segment has to be uniform. It's single valued. A real antenna has a sinusoidal type current distribution. So we simulate that with a step approximation. And the computations are a little complex because the current on one element affects all the current on the other elements back and forth. The output, well, we get the E and H fields by summing the fields produced by the current on each wire segment at a point in space. And we get our input impedance by simply taking the input voltage that you provided, typically 1 volt, and it computes the complex current at that point. And you do the math and you have your input impedance. As I said, important thing is the current is as I said, is assumed to be uniform from each segment. So we have to break it up in segments. So typically each segment on a wire has to be less than 1/10 of a wavelength, but should be longer than 1/1000th of a wavelength. NEC 2 is primarily a thin wire code. It assumes current flows on the axis. NEC 4 is a little bit different. In NEC 2, you can use what we call an EK card, and we'll explain how the cards come about, which actually then calculates the surface of the wire based on the diameter of the wire that you give it. So you actually have to specify the diameter of the wire. And again, another little rule of thumb is that the diameter of the wire has to be small compared to the length of your segments, which helps determine how many segments you have to use. And in general, it's got to be less than 1/10 of the diameter of the wire. If we want to model a solid structure, say you want to look at your antenna over a car, and I noticed somebody had done some modeling in the latest RADCOM that just came today, trying to calculate the fields inside a car for a RADHAZ perspective from their antenna on the roof. You can model that with wire grids. And I've built wire grids for stuff for work that have been like 30,000 segments in a model. So they're quite large, take quite a long time to solve. Another problem with NEC is you need to be careful about wires that are highly acute angles to one another because the current solution doesn't has singularities and breaks down. So what we typically do, if you have a really acute angle, you have to taper the segment lengths, make them shorter, perhaps change the diameter a little bit when you're approaching to make sure that the wires don't overlap with each other. And that's kind of just the nature of the beast. So here's some additional limitations. As I was saying, you can model, say, a structure like a car. You can use plates or wire grids. There are plates. Plates have a weirdness to them, though. They have to be totally enclosed. They can't be open, so you can't have like windows. A plate is a total solid structure when you build it. The NEC 2 code that comes with 4 NEC 2, okay, does not do buried ground radials. And it has problems sometimes with the results if you're using ground radials that are very close to a real ground, right above the ground. And NEC 4, which is a licensed version of the code you have to get a license for, does a lot better in that regard. Another point from my own experience, if you're running insulated wires, the results, when you go off and build your antenna, you'll find your wires might be longer than the bare wires that you can't compute it with. And that's because the dielectric on the wire actually causes the energy to move slower. So the length of a bare wire and the length of a electrical length of a wire that's got insulation is a little bit different. And that can affect the results that you get running your program. You can probably look it up and find out what the small percentage change is, and you can probably adjust for that in building your model by changing the lengths to reflect the electrical length versus the physical length. The amount of memory needed is proportional to the square of the number of segments. And for most of the stuff we're doing for an antenna project, that's not going to be an issue. The code is, most of the codes we're running were written in Fortran. They have to do dynamic array allocations and things. So it's generally not a problem for what you're going to be doing. But if you're building very complex real structures and actually simulating things like, say, for example, chip, then you can start running into issues if you have an extremely large model that, say, has 30 to 40,000 segments in it, it also takes forever to run anything that large. Okay, so let's talk about the program itself. There's really three pieces of the program. There's a preprocessor that builds the model, which basically where you enter your description of your model, your wires, your endpoints, the diameter of the wire. You also enter the commands for it. You tell it where you're feeding the antenna, and we'll go over all this in a bit, the frequencies you're operating at. Then there's the actual computational engine. This is actually written in Fortran for NEC 2 and NEC 4. I believe it's in C for the Magnum, which is the European program. And then they have a post-processor that reads the output file, which is basically an ASCII data file. It can be a very large ASCII data file in some cases. And then performs the post-processing to plot out the results. The actual file will compute, it can actually tell you the current on every segment in your model. It'll give you the currents at the feed point. It'll and you can do the radiation pattern. You can do a full 360 pattern if you wish. Again, that's a very large output file because it's a lot of data points. But most of these programs, particularly for NEC 2, ez-nec, el-nec, are very tightly integrated, and you really don't see this as being a separate steps that you're running. And 4NEC2 is kind of interesting in that it lets you interactively enter most of the commands for your output files. So the user doesn't have to really put the normal required commands in their data file to generate the pattern or generate the frequency sweep to give you the input of your input impedance versus frequency, which we'll actually demo that at the end here. So I was talking about the structure of the card. First of all, this is an old program. It's been around a long time, decades. And it was originally designed for the input file to be on punch cards, okay? And the input file is still basically like a deck of punch cards. So the first two characters on the card tell it what that particular line is. And then the various values go in different fields. With the newer file structure today, we basically use a delimiter of either a space or a comma or multiple spaces. But it'll read those to separate the variables rather than being in a particular column of the card. But the first two entries have to be two letters that tell the program what that card is. So we always start the program with a comment card. It tells you what your program is, CM, and free file text. And you end it with a CE that tells the program, okay, I'm done with my comment. And then you have geometry cards. The most common one is a GW, which is the straight wire. There's other ones that will tell you other kinds of things, and we'll show you those, like a helix or a curve. There's some other special wire cards you can enter. The program itself works in meters, okay? But you can put your data in feet, inches, whatever you want. And there's a scaling card you can put at the end, which will adjust everything you put in to basically to change it to meters. There's also cards that you can use to rotate your geometry. You can actually copy over things, like if you have a complex antenna where you have like 3 or 4 of the same type of antenna, I can actually pick up that piece of antenna with one command and tell it that lines so-and-so through so-and-so my program, repeat that at a slightly different location. So that could be useful for arrays, for example. So after you get done describing your geometry, you enter a geometry end card, and that describes your ground. And then we'll get into that details, and that's at the end here, there's gonna be a lot of interesting things I'm gonna show you about the kind of choosing your ground. And then the rest are the command cards, which tell it what frequencies, okay, where's your excitation applied. Loading lets you put, for example, use real resistance for copper or aluminum, and it'll actually compute the losses in the antenna through the ohmic losses. You can add transmission lines that are useful for things like log periodics or phased arrays. You tell what kind of output you want. You can do a far field pattern. We can do near field E field or near field H field patterns for typically used for red has. And then at the final end, there's an end card that says, okay, I'm done. So the preprocessors basically help you build the models, and post-processors let you look at the dates. So 4NEC 2 actually has, and we'll maybe if we have time at the end, we'll do a demo of these. It has 4 different editors, and you can select which one you want to use. Quite often I use NEC Editor 2, the last one. The first one's just basically a notepad. And so if you really know what you're doing in all your commands, you can just use that and enter the text. There's also a very graphical type of data entry one as well that you can use. And these are all kind of unique to 4NEC 2. There's also a separate tool that comes with the program, a separate program that you can build grids and boxes and cylinders and paraboloids and other structures. So yeah, you can build a dish antenna in NEC. And there's a real convenient routine to do that. That's part of 4NEC 2. And as I said, 4NEC 2 earlier is unique in that you can define variables and constants and use those. And it also does things like it recognizes like number 14 wire instead of putting 0.0058333 feet for number 14 wire. As I said earlier, delimiters can be spaces or commas. Then the if units is meters, and you can convert them at whatever with a scaling card. We already talked about the CM card. 99% of your structure is a GW card, which is basically a straight wire. And the way that works is you put in GW, you put in a tag, which identifies just an arbitrary number of your wire. So you know which wire it is, wire number 1, number 2. The number of segments you want to put on the wire, and then the 2 endpoints, X1, Y1, Z1, X2, Y2, Z2 are your 2 endpoints, and you put the radius or diameter of the wire in. As I said earlier, there's also some extra things. You can generate a helix, an arc, a cylinder, the surface patches, are also geometry entry points. GS scales it, so in the case if I'm entering feet, you can see here my line after I put all the geometry in, I put GS 0.3048, which means that, hey, I'm putting my data in feet, and the program will automatically know to convert that into meters. The GE card's important. It tells it what kind of ground is used. So it's geometry N, but it also tells the program what to expect for a ground. So if I say GE 0, I'm modeling my antenna in free space, no ground. If I tell it GE1, then I'm saying use a ground with currents at ground matching their image. So this is kind of like I get a perfect, like a quarter wave dipole looks like a half wave dipole with half of it below the ground. And GE-1 is use a ground, but with all currents going to 0 at ground. So at that point, and there actually are then 4 different kinds of grounds, and we use a GN card to actually tell it what. So, and this gets kind of important, and we'll show you in the end of the presentation some examples. So GN-1 is what I put in if I'm doing free space. If I want a real ground, I can use a GN0, and the 0, as you can see here, 0, 0, 0, that I put the value of permittivity in and the value of conductance for the ground. And this could also allows you to use a ground screen. If you use GN1, it tells it's a perfect ground. So you're sitting over top of a large metal mesh. So maybe this might be useful for a VHF antenna sitting on top of your car roof. You might want to use a GN1. GN2 is uses the Sommerfeld-Norton approximation for a real ground. This is probably the most commonly used one. Again, you enter GN2, then a 0, 0, 0, and then the next data is the permittivity, which around here is about 13, and conductance is about 0.002 Siemens around here, 2 millisiemens. So that's typically what you would put in, as I can show you here. So this is, if I'm modeling my antenna here in Fairfax, I'm going to put a GN20015, which is, or 13, or something there about there, which is the permittivity of soil around here, and 0.002, which is our ground conductivity, which is pretty lousy, but it is what it is. 4-nec2 also has a different type of ground that's not in the normal versions of NEC. It's GN3, and again, we put the same thing in with permittivity and conductivity, and this uses an approximation that they developed for mini-NEC, and this works better for vertical antennas than using the Sommerfeld-Norton approximation, which will, with NEC2, which we'll show you at the end of the presentation. I'll give you an example of that. And then, as I said, we have an LD command. LD lets us, for example, put real resistance in. So we put the conductivity in moles per meter. So what this does, it lets us say, hey, I got copper, I've got aluminum, and the code will actually take that into account in computing the field level. So it'll figure the losses in your antenna. We also can add LRC and impedances. So this is very useful if you want to model a trapped dipole. So you can add a series LRC network or parallel LRC, which would be a trap, for example. Also, it has a version with distributed properties that might work with transmission line type devices. Or you can put an impedance in simply a R plus JX format, the parallel impedance format. There's also another command called NT that lets you add a 2-port network between any 2 segments. And we have a special command, TL, which is a lossless transmission line that we can put in, and we can connect segments. And where I would use this is, for example, if I were to model a log periodic antenna, where I need to do that. So you have to have, you really have a transmission line with elements distributed across the transmission line with a log periodic. Also useful for phased arrays. EX card tells it the excitation. Usually we use EX0. We tell it the tag number, which wire number it is, basically the segment on that wire that we're applying it, and typically applies 1 volt, although there's options now for putting other than 1 volt on that segment. It can also, rather than exciting the wire, we can just build an antenna structure like a receiver, and we can launch an incident wave. It can be a plane wave, a right-hand or left-hand polarized wave. We also have the ability to inject a current into an element, and also another voltage source model that uses something called a current slope discontinuity. And you can have multiple sources as well. So you can excite more than one node in your antenna. And then finally, we have a frequency card that tells it, okay, here's my frequency. So here's the way that works. I put in FR, tells it, okay, this is a frequency. IFR tells me if I'm incrementing my frequency, is it doing it additively or as a multiplicatively? NQRF is the number of steps I want to step the frequency. For example, if I want to go 7 to 7.3 megahertz and 0.1 hertz increments, I would probably put in, a value of 4 here. And then you put in the first frequency that you want, the lowest frequency basically, like 7 megahertz. And then the step size would be like 0.1 megahertz. So that's how I tell it how to scan and frequency and compute for results for different frequencies as we go through. Now NEC4 does this automatically for you, so you don't normally actually have to put these in, but you do for regular NEC. So the RP is tell us to do a far field radiation pattern. It's performed using spherical coordinates, and there's various options. Again, with 4NEC2, you don't need to worry about this. It does it for you. The same thing applies to NE and NM. Again, these are commands that would tell it to generate the near electric field, near magnetic field, kind of over a grid. And you would use this, for example, for a RADHAZ assessment, where you're looking at the field levels around your antenna. Again, 4NEC2 automates this for you, so you don't have to get involved in these details that you would if you're running the normal NEC codes. So here's a little bit of errata. There are a number of details and options. Generally, you don't need to use, but are well documented. One is, of course, I mentioned the input card of NEC2, which uses the diameter of the wire to get the current on the surface rather than otherwise it assumes an infinitely thin wire at the center of where the current is from. NEC4.2 lets you use SY simple command, and that's very valuable. It's not something that's in the normal NEC codes, but it lets you easily change values, and it can be used as when you're running an optimization. So you can easily change your input file by just changing one parameter or 2 or 3, 4 parameters without having to go down and re-edit your file. So let's take a look at some examples here so we can see what we're doing. This is my 40-meter delta loop. I made a decision to have a horizontally polarized one instead of a vertically polarized one because the vertical versus horizontal, normally the vertically polarized has a much better takeoff angle, but we have really lousy ground conductivity around here, so it doesn't make that big of a difference. And the other issue is I have a lot of trees, and trees tend to affect vertically polarized signals more than they do horizontally polarized signals. So what I did is I used the program to basically, I had a fixed, circumference of wire, but then I changed the length here up and down and moved this bottom wire up and down relative to the apex to see if I could get the optimum impedance matching for what I did. So this is the way it works. So here's my CM comment command. This is the input file, what it looks like. It says, 40-meter delta loop. End command for end the comments. And then my 3 GW commands describe my 3 wires, 1, 2, and 3. These are my coordinates in feet. So basically, well, actually, this is my number of segments. So this is 60 segments starting at 0, 0, 0. It's just my reference point, which is the apex here, really, at 60 feet above ground. And then the other point is at 0 for X, 28.1 feet out, and 28 feet above ground. And then here's my radius of my number 14 wire in feet. Similar thing for the other wire, just a mirror image of the other one. You see here I have a minus 28.1. And then this is my bottom wire. Now, one thing I did here, you notice I'm making this 81 segments. Well, why am I making an odd number of segments? Well, that's because I'm feeding it. And if I really want it to feed in the center, I have to feed it at a segment. So if I have an odd number of segments, then I'm feeding it right in the center, and I've got 40 segments on this side, and I've got 40 segments on this side of my feed point. GE minus 1 is, of course, the end of geometry. It's also telling it what kind of ground I'm using. The loading here tells me that I'm using copper wire, basically. The GN command is, again, telling it to do this calculation for the real ground. EK for this program is telling it to use external kernel. So it does the current on the surface of my wire rather than the center. And then EX is my excitation point. So I'm feeding it at 0, tells it I'm feeding 1 volt into the excitation point. 3 says I'm feeding wire number 3, this one here, okay? 41 means I'm feeding the 41st segment in my wire, which is the center one here. And then the frequency command says I'm just going to run this at 7.18 megahertz at one frequency, at which I did this to generate my little 3D plot of my pattern. And then the RP command tells it to generate the pattern, which is, you know, telling what steps and where to start. And then EN is my end the file command, basically. So this is 4NEC2's visualization of my antenna. This is my delta loop, what it looks like in a 3D antenna pattern. And I'll bring this up more in real time, and we can show you how you can rotate it and look at it when I get out of the PowerPoint. This is my elevation pattern for my loop antenna. You can see here, there's a 0 dB gain, there's my 6 dB gain. So this thing's got about 5 dB gain up here at close to 45 degrees, and then kind of drops off. Again, part of the problem is it would probably do a little bit better if I had a little bit higher above the ground. So let's look at our feed points. So I did a comparison here of calculating this with NEC 2 and NEC 4. And they both are they're a little bit different displays, but let me show you what we got here. So if I look on my impedance plot here, my resonant frequency, where I have the reactance, which in this case is red, you'll notice that I'm going to 0 right at about 7.24 megahertz or so. It's where the antenna is resonant. You see my impedance is around 200 ohms, the real part. On my NEC 4 modeling, which is a little bit different display, again, 0. And the blue line in this case is my reactance. So again, I'm getting a resonant frequency right around 2.5 megahertz. So they agree with one another. And again, this is my real part of my resistance, which is about 200 ohms plus or minus. And then these plots are the same data except expressed in terms of the total Z and then the phase angle. And again, you can see my feed point impedance around 200 ohms and this one about 200 ohms. So they agree very closely with one another, running the same data file on both computational codes. And what I do with the antenna is I put a 4-1 balun at my feed point. So it has a very broad band. So this 200 ohms you can see here transforms down, divided by 4, and I have a very nice broadband response of my delta loop. And I came up with the optimum dimensions using the modeling tool. Okay. So let's go on. Let's look at another antenna. So this is my top-fed, top-loaded vertical for 160 I was working on designing. So this is my vertical element here. This is my feed point, and the vertical element here actually is a piece of coax. But so this is a 2 pieces of wire that run from the top to resonate the antenna on 160 meters. And these are my, I put down for this purpose of this model, I got 4 ground radials here. So again, I start off with my comment cards, CM blank there, CE, and the comments. And then I have 7 wires, right? 1, 2, 3, 4, 5, 6, 7. And I've, again, numbered them 1 through 7. And put number of segments down. So number 1, my vertical is the taller wire, and I made it 65 segments because it's 65 feet tall. So I have 1 foot segments. Each segment length is 1 foot. And again, my GS scaling is to get from feet back to meters. And GE card. Now this one's got an LD of, again, for copper wire again. And again, my ground for real ground here is the parameter EK card. Excitation is at the top, so it's the end segment here right at the top, the 65th segment up from the bottom. And my frequency in this case is 1.85. And again, the RP is the command to do radiation patterns. We don't really need to do that for NEC 2, but I do for the other versions of NEC I run. So let's look at our patterns. So I'd used 2 different grounds when I ran this. I ran one with the Sommerfeld type real ground, and I used another one using the mini NEC ground. So if you look at the difference in here on your screen, you'll see using the real ground, my peak probably, this is -3 dBi, so I'm probably about -4 roughly is my peak gain. So this is not a greatly efficient antenna, but again, it does have relatively good gain at low elevations. With the mini NEC ground, my scale's a little bit different here. So you'll notice this is -1 here, and this is 2. So this is about 4. So on my gain here is a little bit less than 0 dB. So I've got quite a difference in the actual levels. The pattern is kind of basically the same, but the losses and the levels predicted are different for NEC 2 depending on which ground I used. And in this case, they generally recommend using the mini NEC ground if you're doing verticals. So for something like Mike's 160 inverted L he was talking about at our previous meeting, if he was to model it, he should be using this ground, not that ground. And since NEC 4 does a much better job of this, I also ran it with NEC 4. And again, you can see here, this is 0 dB guy on the outer circle. The inner one's -5. So again, my peak gain is a little bit below isotropic, but it's probably about -1.5 or so dBi. So this code does has more accuracy dealing with radials close to the ground than the other ones. But as you can see, the mini NEC code is pretty close. So let's look at our feed point impedance here. So again, I ran 4 NEC 2 with a real ground and 4 NEC 2 with the mini NEC ground. Well, it has got quite a difference here. Okay, so my reactance, or where my resonant point for this one is, according to the real ground for this geometry, is up here. Oops, where's my cursor? About 2.12 megahertz. And the green, and you can see here my with the top feeding my resistance parts pretty close to 50 ohms in the 160 meter band. But you know, the minimum VisWAR and all is going to occur down here around 2.1. Okay, so it looks like the antennas may be too short. Let's look at a 4-nec 2 mini neck ground. Well, wait a minute. Look here. My resonant frequency of the antenna, that is where the reactance is 0, according to with this ground model, is 1.86 megahertz. Quite a difference from the other one. And again, when I come down here and start looking at my magnitude, you know, I'm pretty close to 50 ohms from 1.8 up here to 1.9, right? On this guy right here. Whereas this one, I'm not even close to 50 ohms. So the type of, this is this identical wire model run with just changing the type of ground. So selecting the appropriate type of ground to use becomes kind of important when you're modeling. And if you're modeling things like inverted L's and verticals with some sort of a ground screen or ground plane, you got to be pretty careful with these models because they do get you different results. So again, I did the same thing with NEC 4. And once again, in this case, the colors are backwards. So the blue in this case happens to be my reactance value. And you can see I'm resonant more about 1.84 megahertz according to NEC 4 with the same design. And again, my feed point impedance here is pretty good for 160 meters with this design. You're pretty much 50 ohms, close to resonant right here. And again, this is the magnitude phase plot of the same data. So again, you can see the input impedance, whereas the red line is my magnitude, again, very close to 50 ohms here, and the blue line is the phase angle of that. So that's kind of the show. Now, what I'm going to do next is actually want to go ahead and actually launch the real program. And I'm kind of figure out, I probably have to stop sharing for a minute so I can see my screen to do that. Let me get NEC down here. Okay. So let's go over to my, let me go back to share my screen here. So I'm going to launch the program for NEC 2 right now. And let's see, my script, I'm probably not script. See if I've got my screen sharing up here. So are we up yet? I think so.
Yeah.
Yeah, so I'm up. Okay, so this is what the main menu looks like for 4-nec 2. When you bring it up, it always has an antenna there. You can't start kind of blank. So you can do an open the file, and it has a subdirectory here, as you say, called models, right? And so they have all these models you get with the program. HF beams, fractals, aperiodic, VHF, UHF, almost anything you want. So I'm just going to, I have it without a forethought to this. I'm going to just go to HF beams. And here we have a bunch of different ones that people have contributed. Some of them are ours. Let's take the 20 meter Moxon here. So to, again, show you how to enter the files, we're going to go to this, which is the editor. And this is antenna, as you can see here, that's actually designed by L.B. Seebeck, who's no longer with us, but was a very prominent guy. This is the plain vanilla input file. You can see the total file here. I can change my settings and go to a different editor, like the NEC editor. And let me bring that one up to show you the difference here real quick. So this one actually kind of lets you more of a spreadsheet. So you put your wire in, tag number, lets you build it. Your source and load, again, in this case, his tag, wire number 223 is his source voltage. He has copper specified, frequency ground. He used something called fast ground in this particular one, but if I really want to look at this, I can do real ground, and I can pick either average, or they have different default ones you can pick. Here, as you can see, fresh water, all kinds of stuff, marshy flatland. But I'm going to put our real values in here. So I put user specified, and this is going to come up with 0.05, and ours isn't quite that good. Ours is more like 0.02. That's good for that. Others, okay. So this is a 20-meter Moxon. So checking that, okay. So I'm going to use this geometry. I just modified the ground. There's a little icon here that says run NEC. I can click that. So I'm going to do a far field pattern on his Moxon right now, this file that I just pulled up. All I have to do is click on far field pattern and hit generate. And up here appears his pattern. This is his vertical pattern for his Moxon. That's the horizontal pattern for his Moxon design at this frequency of 14.18. If I want to be fancy, I can do a 3D view of this. So this is a picture of the Moxon. I can tilt it, and you can see the Moxon here above ground, right? So let's look at the pattern. So I can go to pattern. I can do multicolor, for example. And I'm going to turn the ground off. And then I can, this is the pattern from the antenna. So I can swing it around and rotate it. The colors are the relative levels. You can see here the bright pink corresponds to like 10 dBi. I can hit the zoom button to make it a little bit bigger. But anyway, so that's, look down on top of it. So that's kind of looking down. There's the feed point, the reflector. So that's the antenna, and then this is the pattern around the antenna. Okay. So this is what you can do in this nice free software. I'm going to close that window. Let's run it again, but I'm going to do the VisWire check. So what I do for VisWire is I hit frequency sweep here. Okay. And I can put in the start frequency. Let's start at 13.9, since this is a 20-meter antenna. We'll end it at 14.5. I'm going to step in 100 kilohertz increments. So all I do is just hit my generate button. And so this first plot gives me the reflection coefficient and the SWR. So you see here, there's 2:1. So this antenna works out pretty well. If I want to look at in terms of impedance, instead of looking at VisWire, I just click on the impedance here. And again, this is the reactive part of the impedance. This is 0. So you can see here, this particular antenna happens to be resonant at 17.151 megahertz. And you can see how the feed point impedance varies, around 50 ohms as you go up around throughout the 20-meter band. So Anybody have any questions at this point?
Everybody still there?
Anybody still there?
Just make sure you hit your unmute button if you do have a question.
Well, I have a question. This is Roger.
Sure, Roger.
And given the drastic differences based upon your different assumptions about... that wasn't me.
Yeah.
Given,
Mike,
given,
you might want to mute.
Given the drastic differences in the outcome in the models as a function of choice of ground models, and you mentioned, I think it was the Norton, I don't recall.
Norton Sommerfeld, yeah, that's
is often the appropriate model to use, best model to use. Is there any other criteria just by examining the plots to say, gee, it looks like this is a more realistic or appropriate ground model than this
well,
is?
what I have to show is if we're dealing with something like this model here where we have this moxon up in the sky, it probably doesn't matter. The only problem we get into, we got to be careful of, is where you have wires or radials that are close to the ground. And in the case of 4-nec 2, that's why they provide this, quote, mini-nec ground. Because if you're modeling, for example, your inverted L or some other vertical antenna that's with radials sitting on or just slightly above the ground, then you need to use that particular ground model rather than the Norton Sommerfeld approximation with nec 2. From what I've been told, nec 4 supposedly gives much more accurate results than nec 2 does for that set of circumstances. But what they did provide you with 4-nec 2 is this mini-nec ground, which was a different ground interaction that was developed by the guys out at the time NOSC, which is now part of Spaywar Pacific, which is now part of NIWIC, and it's quite a
yeah, it was NRAD back in the day.
Yeah, and yeah, right, exactly. Well, even before then, it was NOSC way back when they were developing this stuff, and so they used their ground approximation to add that in for using it with the verticals. So as you can see, it's not precisely, it doesn't come precisely the same, but it comes pretty close to the results of nec 4. But if I'm modeling a dipole, I'm modeling a Yagi up in the air, I'm modeling the moxon, a log periodic array, it probably does not going to make any difference. And that's kind of what I was trying to show in the first example I gave, where I took my delta loop and I got the same result, basically the same feed point impedance, the same pattern with both nec 2 and nec 4.
Whoops, my last comment would be, given the proper parameters, you could also model the tape measure antennas, which Ron Payne loves to demonstrate and which work quite well. I think Kirk showed me a KM4JOA, a tape measure antenna, a small Yagi that he was using in an RDF experiment. And that would be interesting to try to model something like that with a tool like this. Just a comment. I wouldn't know how to do it myself.
Yeah, well, as I said, probably what you would do in a case like that is I would actually do it as a surfaces. So I would break it up in small little, measure the tape. So rather than having the tape be a wire, which it's not, I would actually model it as being more or less a flat surface. So I could actually do that by basically making a wire grid. Again, same criteria, the area of that grid's got to be less than 1/100th of a wavelength. But I would just model that. I could actually model the flat measuring tape, because now we're talking about, not a round wire, but a flat element. So yeah, the code can definitely do that.
Thank you.
Are these antennas modeling looking at or assuming you are a wavelength off of ground, or?
No, these are based on real heights above ground. For example, let's just take this example right here. I can change the height of this on the fly. So this is our current pattern. So what happens to this antenna if I push it closer to ground? So I can come in here, open up my editor, go back to geometry. So right now this is at 10.668 meters, I think. Yeah, scaling is in meters. I can cut that down to, I don't know, 3 meters above ground. Let's see what happens. I'll do this in real time here. Okay. So instead of being 10 meters off ground, we're going to make it 3 meters off ground. So part of the reason for using this antenna modeling code is it does account for the ground effects. And that's one reason it makes it powerful to use, because you can see how things change with height above ground, and you can change your dimensions on your antenna, and you can change, in my case, when I was building the delta loops, to get the feed point impedance in a reasonable pattern, I could do that. So I just made these changes. Now I'm going to run this program, and let's do the far field pattern first. Okay. That looks quite different than it did before, doesn't it?
Yes.
You can see all of the energy now is going very much closer to ground. Our energy is going up at a high angle, almost 70 degrees, well, 60 degrees off where our main lobe is, where before it was down here. So this, accounts for that. And if I want to look at the horizontal pattern, I don't have quite as much directivity as I did before either. So, and I can change on the display. All you have to do is hit the space bar, and I can go from vertical to horizontal pattern like that.
And if you're modeling an end-fed long wire that is not horizontal but slopes towards ground?
Yeah, I mean, it's fine. Again, I would, in that case, I would definitely be careful about using the ground, because again, you have a wire close to the ground. So I would stay with the mini nec ground, or if you have access to it, nec 4, because nec 2 might be a little bit off, particularly in the feed point impedance and things. The pattern probably is not going to be as far off as the feed point impedance calculation.
And Lee, just in general,
Yeah.
if somebody's starting out trying to model their antennas, the pros and cons versus the ez-nec, the free version, versus the 2N4 or 2,4N nec version that's available. What would you recommend if somebody just want to get, start playing out with like a dipole or something and modeling some stuff? What would you think would be best for people to start with?
Well, I think the 4nec 2, as I said, it has the different editors. You can select different ways of editing your file. So that has a geometry editor, which let me show you that real quick. So this is more of a graphic thing. I can put my wires in, and I can wire geometry. Let's see here. I don't use this one very often, but this is more of a graphic approach to building your model using this particular editor. There, as I said, there's 4 different editors. You go settings and then select whichever you want. There's another nec editor here. Let me kill that for a sec. Which is more the standard file type thing. The other thing is there's lots of examples that come with this program. So you download lots of antennas that you can look at to understand how other people built their antennas, which gives you a lot of insight into how you do it. I was going to try to use the ez-nec. I didn't have time to actually get it into the presentation. But I really like the graphics, and as I said, the other thing about the 4nec 2 is you don't have to worry about with the calculation. It automatically will do either far field pattern for you. You do the frequency sweep to get the feed point impedance over frequency. You can actually do near field, either E or H field, and it will compute the field levels around the wire. Around, you basically define a grid in X, Y, Z in 3 dimensions, and it calculates either the E or H field levels in that, and then it'll display that for you. So I think the guy over in Holland did a remarkable job of building the preprocessor and post-processor that goes with this program. That really makes it easy to use. And it's, as you can see here, it runs pretty fast for most of your standard antennas. And as I think back here, let me get out of that real quick. Go back to File again and open just, you name it. There are all kinds of antenna examples in here. Low frequency vertical, HF simple, HF short, collinear. So they even have magnetic loops in here that people have built. So these are all you get all these models when you download the code. And multi-band antennas. I'm not see here. There's log periodic, of course. Might be an interesting example. So log periodic, as I mentioned, it uses the transmission lines, right? So you have your elements, and then they're interlaced with the transmission lines. So if you look at that with the editor, you'll see here the TL command. So this is connecting all the elements with the transmission lines for the log periodic. So again, this is and he's using variables here in this code so that you can change these values on the fly without having to re-enter every value in every column, which is kind of unique to 4nec 2. I don't think the other codes have that. Standard nec does not. So there are some easy features to use. Again, you can just put in like number 14 for the wire. You don't actually have to put a numerical value in, and it'll read number 14 as being number 14 gauge wire. And just for grins, that's the model. If we run this real quick, let's see what it does. I'll do a far field pattern. And then again, this is the log periodic horizontal and vertical pattern for this log periodic array. If I do that one in 3D, here's the antenna. I guess in this case, he did this in free space rather than over ground. And then I can put the pattern in, either multicolor, transparent. Transparent looks like that. I can do multicolor, which is, I think, kind of niftier. And I can zoom up on the pattern relative to it, and we can turn it around. So you can see a visualization of how this pattern looks relative to his antenna. So this is a log periodic array in free space. So I kind of like the visualizations in this particular one. And again, I also like the fact that you can easily on the fly, you don't have to give it RP values. You don't have to actually give the frequency values. You can do those at runtime, and the code automatically inserts them and runs it. So it's one less thing that you have to enter as a user.
Leif, got another question for you.
Sure.
Like in field day operations, you've had some really good input on multiple antennas within a field. So if one was to model a particular antenna as a standalone antenna, and then to model another one as a standalone antenna, and you want to combine them within a field.
Right. So there's a routine.
What's the best way to go about that?
Okay. So there's actually a routine, and there's a called max coupling. So you can actually tell it to couple between the feed points of two antennas, and it'll come back with the dB value. So that's actually built into the code. So I've built rather complex models with, say, maybe 6 or 8 antennas on a structure like the top of a ship, and use this code then to compute the isolation between the antennas. So the answer is yes, you can. It has a built-in routine, and there's really 2 different ways of doing it, but the max coupling is built into the NEC code.
Okay,
And
so within this, the software package that you can download, there's something in there that allows you to independently define the models and then combine them together to get a field effect?
Well, you actually build it as one file. So you would build, the 2 antennas would be in the same file.
With 2 different sources and all the rest of it?
Well, you really don't need to do the sources if you're just doing coupling.
Well, if I have like a 40 meter and a 20 meter antenna in the same field, those are separate excitations.
So what it will do is let me bring up ez-nec here real quick. There's another version of NEC that's a commercial product, but the LB was their technical advisor. And as far as I know, the company that makes this one is out of business. But if you look at the command list here for NEC, this tells you all the commands. So this is all the defining all the windows, catenary wires, conversions, surface matches, whatnot. So under controls, there's a control called CP here, maximum coupling. So I can actually couple and compute the coupling between any wires in my model, any 2 wires in the model. So I can take those 2 wires as being the feed points of the 2 antennas, and it will calculate the max coupling between those 2. And I can do that
okay, so for the average Joe, I mean, like me, just you know, at the cusp of trying to learn this, if I'm trying to figure out, I have 2 antennas in a field, how they're going to interact.
Right. So
what's my best approach?
You just build both antennas in your model you just choose your spacing so that they're both there. Okay. Or 3 antennas or however many you want. You can there's no limit on how many other than the size of your memory and the amount of time you want. But the code is fine in calculating out. We can have 5 or 6 separate antennas, and I can do one run and do the coupling between each antenna and all the other antennas.
So I would build in one file all the antennas within that file versus having 2 or 3 different independent files.
And
combining them.
Right. So they all would be in one file, and use this command, which is max coupling. And the way that works, you just put in the tag number, identify the wire number, whatever, for the first antenna, and the segment number, and then the second element and the tag number and the segment number. Now, it'll do these couplings at the frequency you specify. So you have to specify the frequency, right? So
Okay, makes sense.
Right, obviously.
Mm-hmm.
So it's at whatever quote is your transmit one, you specify the frequency, and then you see the power that at that transmit frequency that would be received in all the other antennas.
Mm-hmm. Okay.
So if you have a 40-meter Moxon up there we're transmitting with, and we want to see how much energy gets picked up in the 20-meter Yagi, yes, it will do that.
Mm-hmm.
Now, what it won't take into account is, of course, the feed network and any frequency dependencies in the matching network per se. So it doesn't really do that very well, but it certainly will tell you at the feed point, of the wires, how much energy from antenna A is then picked up at the feed point of antenna B.
Okay. Cool.
So again, this is, and I don't know what models I have available off this one off the top of my head, but this is just another code that I was messing with. Again, my 40-meter delta loops in here, and this is a similar program. It's in this case, it actually runs NEC, and then I can look at my pattern or whatever I want here, like my feed point impedance. So this is just a different program from a different company, which is basically, I think, out of business at this point. But again, this is how that one works. And this is if you let this thing go, it'll start just rotating the model for you in the 3D view here. So anybody else have any other questions we can help you with? Or anything else we can demonstrate here?
Anyone else? Well.
So is everybody ready to go out and download 4NEC 2?
Let's. I think I might try 4NEC 2 out, although a few other ideas as well from this, I will say.
I mean, given it's free and what it does, it's rather amazing, I think. In my opinion.
Oh yeah. I think it might be neat if I get it up and running myself. Maybe we can actually spend some time running through a deeper learning of this software as well for those of us who actually might want to try it out on our own, and then come back and talk to you about it.
Yeah. Well, as I said, the real key to it is building that input file.
Yeah.
And putting in your data. And as I said, let me go back to the other editor here real quick. Hold on. I can select which editor here. I'm going to choose this one because it's a spreadsheet, so it's a little bit easier to deal with. So again, you just sit on paper, figure out your wires, figure out where the endpoints are, figure out how many segments there are based on how long the wires are relative to a wavelength. Each segment's got to be less than 1/10 of a wavelength. Somewhere between 1/10 and 100th is usually pretty good. The more segments, the longer it takes to compute, and the more memory it takes up. But again, that's only consideration if you really get really large models. So just filling out this geometry is really most of it. Then you just collect, again, put in your feed point, select where that is. If you want, you can put real copper in, or you can just have perfect conductivity. And the next thing is put the frequency and the ground type in here. And then you just hit the button. If you want far field. Then you get that. So in this case, let me go back real quick. He didn't have the ground. I can probably add a ground in real quick. Actually, it did have ground, didn't it? Let's see here. Go back to the editor. Yeah, we did use a ground. One other thing with NEC too, I didn't mention this. It says here you use a second ground, so you can use 2 grounds in NEC, and that would be useful in cases like you're at the edge of a cliff, or you can use that with elevated ground radials. So you could actually have like a ground screen around your antenna as the first ground, and then have a second ground, which then you can use, and then you can put in the, as you said here, you have a ground screen that you can set up for the primary one, and then you can do a secondary ground. So you can actually do, if you will, radio, some sort of a ground screen around the antenna itself, and then actually have your real ground. So that's another option that's available in setting up the grounds. So that's another capability of the program that we can do.
Oh, nice.
I do have one more question, quick. I think you've answered this in a way. You said, I don't think you can measure the transmission line effects, but suppose you had an end-fed antenna and you're modeling the VSWR, which would certainly depend upon having a proper 9-to-1 balun. I mean, that's part of the art of designing end-feds.
Well, I mean, there actually is a way of doing that in NEC.
Good question.
It has a
I'm sorry.
capability of you doing transformers.
Yeah.
Let me just say no here. Let me go back to the other. Yeah, I got that real quick. Let me bring back up ez-nec for a second with the command list. Back to our control cards. So let's see here. Pre-current wires, charge, data storage, 2-port networks. So there's the NT command. You can use the 2-port network command to model it, or actually to model a transformer. There's kind of like, if you go out there, there's 2 ways of doing that actually, but probably the best way is with the NT command. So what you can do is, again, you can set up your, you have your input impedance, the transfer impedance, and the output impedance. So you can actually specify a network, in this network, you can make that network a transformer. So you can add a 9-to-1 balun or a 4-to-1 balun or something if you want,
Yeah,
actually into it using the network command.
That's very cool.
I gotta say, this was a son of a gun for me. Can you hear me?
Yeah, go ahead, Mike.
Yeah. So ez-nec has this built-in, this transformer capability, but the this program does not. I have some really good information I've recently learned on how to do this, but it was not straightforward. So if anybody wants to know how to do this, you can hit me up and I can send you some details on this.
All right. But in the normal NEC, this is kind of the way you go about it, is you use the network.
Yeah, but I mean, entering these values for the Y11, 12, and 22
right.
wasn't clear to me.
Okay.
It took a lot of studying, and and I finally figured it out, but it wasn't easy.
Right. So there is some information out there on the internet on how to do that. So, but anyway, that would be the way in which you would have to do a transformer. So again, it's not a circuit analysis program. you build a structure with wires primarily, and it calculates the currents on every wire, and from those currents it generates the fields. And since you know the currents on every wire, you can do coupling and all kinds of things as well. So it doesn't do everything for everybody, but what it does do is it gives you a pretty good idea of how well your antenna is going to work. And you can optimize it like I have. You can change dimensions, and in my case, like the 40-meter delta loop, I actually played with the angles and the length of the endpoints on the bottom wire and moved them up and down, and keeping the loop the same circumference till I got the wonderful 200 ohm feed point impedance and with a reasonable pattern. And I said, great, I have a with my 4-to-1 balun, I've got a very low VISWAR across the whole band. And then I discovered, by the way, I ran it on 20 meters, and guess what? It works on 20 meters. A little bit higher takeoff angle, but it actually matches pretty close to 50 ohms through the balun on 20. So I can actually use this antenna particularly for short skip on 20 meters. I can use my delta loop that was designed for 40, I found out.
Lee, is there any iteration stuff like you can say, like scale a particular wire over, plus or minus a certain percentage or something, or is it all?
Yeah, there is a optimizer function right here. You can see F12. Oops, please go to it first. Okay. No. So there actually is an optimizer under calculate. So there's an optimizer routine built in. So so here's a weighing factors of gain versus VISWAR, front to back, front to rear, RN, RX, efficiency. And I don't have a whole lot of experience running the optimizer in it, but it actually does have an optimizer in it.
Okay.
That's built in, as you can see here. Target is 50, okay.
Because I was thinking more along the lines of, I know, ez-nec, there's a ham that runs a spreadsheet optimizer or something where you can vary a particular parameter over a range and plot various stuff. I haven't used it, so
right.
I can't give you much I can't speak much to it, but
so it has
a really nice optimization.
Yeah, I've not really used this function very much, so I really can't. I'm not an expert on it, but it does have an optimize or evolve, sweep, convolution test.
Okay.
Options, default.
I didn't know this was here. This is good. Thank you.
So it does have an optimization built into it. I just have not had much experience running it.
Mm-hmm. Okay.
I have to do some reading the manual here for some of this stuff because it's not things that I've actually used in the past.
A lot of stuff in there. Yeah.
But it does have the capability. And again, for something that's free, it's to me, it's quite a.
It's amazing. Yeah.
Amazing. Yeah. So let's see. Where are we at, Andrew? Anybody else? Any other questions?
That's where we're at. Does anybody else have any other questions? No, I'm not hearing anything from the gallery. So if that's the case, anybody who does have any other further questions about this, I think we all know how to get in touch with Lee. So you can definitely reach out to him and learn a little bit more. I probably will try to do the same in the near future. But otherwise, thank you all for attending. I think we had actually some very good attendance. I think at one point we counted up to 60, if I'm correct. So seems like we're going well for our virtual meetings. Excuse me. Well, I think that's about it for this evening. So I look forward to hopefully seeing you all at the next one. I think we'll probably be planning on another virtual meeting in a couple of weeks. I don't know that we'll have the ability to be in person just yet, but I hope to all see you once again there, and I think we'll have a couple of interesting presentations then.